Bismillahirrahmanirrahim. Today I'm going to talk about complex numbers. So we all know that there are simple quadratic equations such as x squared plus 1 is 0 that have no real solutions. So x squared plus 1 is 0 have no real solutions. In order to provide a notation with which to discuss such equations, we introduced a symbol I and define. So we have a symbol I, and we say that its square is -1. Okay. Now a complex number is defined to be a symbol. A complex number is defined to be a symbol a plus b iota, where a comma b are real numbers we denote a complex number is if z is a plus b iota, then a is real part of z and b is the imaginary part. So we can also write a is re of z and b is im of z. Something like that. We can define the addition and multiplication of complex numbers by the following rules. So we define the addition by this rule that a plus b iota plus c plus d iota can be added by adding reals to reals and imaginaries to imaginaries. Multiplication. We can multiply two complex numbers as follows, that AC minus BD plus AD plus BC iota. If you use this formula, if you multiply these two brackets, you will get this kind of thing. So we can use this formula to multiply the complex numbers. Now notice that in the multiplication rule, we multiply out the brackets in the usual way and replace the iota square by -1. So over here, the minus comes from the multiplication of b and d and iota. So if you multiply these two terms of this bracket, you will get iota square bd, and then iota square, as we have already said, that is -1. So you will get this minus because of that iota square in the formula. Okay. And similarly, if you just say, for example, you have 1 plus 2 iota and 3 minus iota, you will get what? AC, which is 3 minus B and D, which is minus here, but you can replace B and minus 1, okay? Because this is minus. So when you multiply these two brackets, there is no minus sign inside here. So if you have minus 1 here, minus here, that means you have minus 1 as the value of D, okay? And then you can say plus A and B, which is 1 into minus 1, plus in the formula B into C, which is 6, and you will have iota here. So this will be equals to 3 plus 2 plus minus 1 plus 6 iota, and that will be 5 plus 5 iota. This is how we can solve the multiplication. And if we have this, that a plus b iota is multiplied with a minus b iota, and that can be written as a square plus b square. And this is a very useful formula we use to solve it so many equations. It's also possible to subtract. You just have to replace the sign, and less obviously to divide them, provided CD are not 0. So let's write subtraction also can be written as a plus b iota minus c plus d iota is a minus c plus b minus d iota. This is subtraction rule. And if you want to write the division rule, you have to say for c comma d not equal to 0, we have a plus b iota over c plus d iota, and this can be written as, so remember over here we do the rationalization, so we will do that a plus b iota c minus d iota over c plus d iota into c minus d iota. Now we know this rule, so we'll just write. So we know the multiplication formula, but like there we have c plus d, now we have c minus d. So in that case, we will have ac plus bd over c square plus d square plus bc minus ad over c square plus d square, and this have iota with it. So if you use this multi-division formula, you will get something like, for example, 1 minus iota over 1 plus iota is nothing but 1 minus iota to 1 minus iota divided by 1 plus iota into 1 minus iota. And this is, if you just multiply these two, you will square them. And so you will end up with minus 2 iota over 2, which is minus iota only. Now we write C for the set of complex numbers. We write like this, or like maybe more. C for the set of all complex numbers. And if we identify the complex number a plus 0 iota with the real a, we see that. So if z is a plus 0 iota, then this shows the reals are subset inside the complex. Now notice that every quadratic equation, notice that every quadratic equation for A, B, C in R has roots in C, because every real is a complex number. Now, by the famous formula, we will familiar with the roots are what? The roots are 1 over 2a minus b plus minus under root b square minus 4a c. Okay, this is the famous formula, and from there we can always find the roots. So now we say if b square is greater than or equal to 4ac, these roots are in R. If b square is less than 4ac, they are complex numbers. Right? And then we can say minus b over 2a plus minus under root 4 ac minus b square over 2a iota are the roots. These are the complex numbers. So okay, perfect. Now we want to talk about the geometrical aspect of the complex numbers. Geometrical representation of complex numbers. Now, we know that it turns out to be very fruitful idea to represent a complex number by points in the xy plane. Now, this is done in a natural way. The complex number a plus b iota is represented by the point in the plane with coordinates a comma b. So is by the point in the plane with coordinates a comma b. So let's draw the plan. Okay. And for example, I is represented by what? Iota is represented by 1 comma 0, then minus iota, then 1 minus iota by 1 comma minus 1, and so on. So we denote that here we have I, and we go further here. So in parallel to this line, here we have 1 plus I, because here at this point we have 1, and similarly from this point down here we have 1 1 minus iota. Okay, now if z is a plus b iota, we define z bar as the complex conjugate. Now if z is a plus b iota, we define z bar is a minus b iota, and call this the complex conjugate of z. Also, the modulus of z is a plus b iota is the distance from the origin to the point a comma b representing the complex number z. It is written as the modulus is written is mod of z, and we compute it a plus b under root a square plus b square. Now notice that product of z and its complex conjugate is nothing but a plus b iota into a minus b iota, and that is a square plus b square, and that is the modulus of z square. Okay. What about the argument? The argument of z is the angle theta between x-axis and the line joining 0 to z measured in the counterclockwise direction. We can do that. We can do that as follows, that we have this system theta. This is R. This is Z is A plus B iota. This is B. This is A. Or we can do, that as follows. That we have this line down here. We call it Z. Now the theta can be measured is the counterclockwise, starting from here to here. Like this. And this is going to be theta. Okay. Now, if Z is A plus B iota, if Z is A plus B iota, and mod of Z is just R, then we see that A is R cos theta, comma, B is R sine theta. So Z can be written as R into cos theta plus iota sine theta. And this is known as, this is polar form of complex number. This is polar form of complex number Z. We can do an example. So the polar form of I, the polar form of iota, -1, 1 plus iota, and 1 minus iota R. So iota can be written as 1 into cos pi by 2 plus iota sine pi by 2. You know, this R can be measured as under root A plus A square plus B square. And then you have cos theta plus iota sine theta. So you can measure the theta like that. Similarly, we can write -1 is equals to 1 into cos pi plus iota sine pi. You can measure 1 plus iota is under root 2 cos pi by 4 plus iota sine pi by 4. So then we can write 1 minus iota as under root 2 cos 7 pi over 4 plus iota sine 7 pi over 4. Okay. Then let z is or cos theta plus iota sine theta. Notice that we can write cos theta plus iota sine theta as follows, that cos theta plus 2 pi plus iota sine theta plus 2 pi. Or you can write cos theta plus 4 pi plus iota sine theta plus 4 pi, and this goes on. So the multiples of 2 pi can be added to theta or subtracted from theta without changing z. Thus, z has many different arguments. This means thus z has many different arguments. There is, however, a unique value of argument z, value of the argument of the z in the range between minus pi theta, and we call it the principal argument of z is minus pi less than theta, theta less than pi, or equal to. And we call it argument of z. For example, argument of 1 minus I is minus pi by 4. Minus pi by 4. Okay. There we end our first part of the lecture of complex numbers. We'll start again in the next part with De Moivre's theorem.